The aim of the first experiment is to determine the ethanoic acid content of vinegar. Now, as you should know, vinegar is just a dilute solution of ethanoic acid. So the concentration of ethanoic acid in the vinegar can be determined by titrating it with an accurately known solution of sodium hydroxide. Therein lies the problem, however. Sodium hydroxide is not a primary standard. It's not stable enough. It absorbs water very readily from the atmosphere, and it reacts with the carbon dioxide in the atmosphere as well. So before determining the ethanoic acid content of the vinegar, we need to work out the exact concentration of our solution of sodium hydroxide. This will be done by making up a standard solution of oxalic acid. Now, oxalic acid is a primary standard, so we can make up a solution of accurately known concentration of oxalic acid. We can then use that to work out the exact concentration of our sodium hydroxide solution. And then using the sodium hydroxide solution, we can work out the concentration of ethanoic acid in this vinegar by titration. So there's 4 distinct steps to this experiment. So the first part of the experiment is making up a standard solution of oxalic acid. The second part is using the oxalic acid solution to determine the exact concentration of our sodium hydroxide solution. In the third step, we'll use the sodium hydroxide solution to determine the ethanoic acid concentration in the vinegar sample. And in the fourth step, we'll check the validity of the method by analysing a control sample. This is a sample which we know the concentration of the ethanoic acid, and can we use it just to check that your method actually did give reliable results. So what I'd like you to do now is to watch 3 short videos which demonstrate how to carry out this experiment safely and accurately. So in the first part of the experiment, we're going to make up a standard solution of oxalic acid. Now, oxalic acid is a primary standard. It has the formula COOH twice, and it looks like this. Cut that. Okay, so we get a clean 100 cubic centimetre beaker, put it on the balance, wait till the reading settles down, and then tare it. So it's reading 0.00. The third decimal place might flicker around a bit, there's not much we can do about that. We now want to add approximately 3 to 0.0 grams of the oxalic acid. Okay. It doesn't need to be exactly 3.2 grams, but we do need to know exactly how much we do add. Be careful not to spill any of it on the pan of the balance. Yeah, that's close enough. So 2.973 grams. Okay, so now that you've measured out your oxalic acid, it's important that you immediately record the result in your data booklet. So 2.973 grams.
Fine.
Right, the next thing I want to do is dissolve the oxalic acid and transfer it quantitatively into a 250 cubic centimetre standard flask. So it says in the instructions, add approximately 50 cubic centimetres of deionized water. So I'm just going to use the markings on the side of the beaker to judge approximately 50 cubic centimetres. Okay. And now we want to get that fully dissolved. So it's going to take a few minutes with a bit of stirring to get this all fully dissolved.
Right.
Okay, so that looks as if all the oxalic acid is completely dissolved. Now it's important when you take the glass rod out to wash it down so we're not losing any oxalic acid. We're then going to transfer it into a 250 cubic centimetre standard flask using a funnel. And we're going to wash down the sides of the beaker and transfer the washings, and we'll do that a couple of times. And we can be pretty confident now that we have transferred all our oxalic acid into the 250 standard flask. So next thing to do, actually I'll keep that back in, is to make this up to the mark, which is approximately here. So don't need to be too careful at first. But as you get to the start of the neck, you'll want to start doing it far more carefully. Okay, so as we get near the mark, start adding it more slowly, and then at the very end I'm going to add the last few drops using a dropping pipette. So the bottom of the meniscus is right at the mark. And I think that looks pretty good. Yep, I'm happy with that. So the final thing to do is just stop with the flask and invert it a couple of times to make sure the oxalic acid is homogeneously mixed throughout the solution. And label your beaker with your name on it so it doesn't get confused with any other groups. Okay, so the number of moles of oxalic acid is given by mass over the GFM. So 2.973 divided by 90 is 0.0330 moles. So the concentration of our oxalic acid solution is the number of moles divided by the volume. So 0.0330. The volume was 250 cubic centimetres, so that's 0.25 litres. So the concentration of our oxalic acid is 0.132 moles per litre. And it's appropriate normally to give your result to 3 significant figures. Now you'll find in your tray a bottle of approximately 0.1 moles per litre sodium hydroxide. Now in the second part of the experiment, you're going to find out the exact concentration of your sodium hydroxide by carrying out a titration with your standard solution of oxalic acid that you've just made up. Next thing we want to do is to transfer 10 cubic centimetres of the oxalic acid solution into a conical flask. But the first thing we have to do is to wash out the pipette with some of the oxalic acid solution. So we half fill a pipette and empty it into the sink, and then we're ready to transfer. So we put the pipette into the solution, suck it up till it's above the mark, take it out of the solution, and then let some back out till we reach the correct mark. Then once we're happy that we have exactly 10 cubic centimetres in our pipette, we can then transfer that to a conical flask, followed with a few drops of our phenolphthalein indicator. The next thing we have to do is fill up our burette with our approximately 0.1 mole per litre sodium hydroxide solution. So initially we have to clean the burette with some of the solution. Then fill it up with the sodium hydroxide solution to above the zero. then run some out. So it's below the zero and the bottom of the burette is filled with sodium hydroxide solution. So I'm now ready to do my first rough titration. So I record the starting volume and I then add the sodium hydroxide in quite quickly because it's just a rough titration. I'm just trying to find out roughly how much sodium hydroxide I'm needing to add. Is it 5 mils or 50 mils? So the solution's gone pink. I record my final volume and I find out that the volume required was 21.4 cubic centimetres. So I'm ready to do my first accurate titration. So I pipette another 10 cubic centimetres of the oxalic acid solution into the conical flask, add a few drops of indicator, and then I'm ready to do my first accurate titration. So I record my initial volume. Add just under 20 cubic centimetres quickly, since I'm pretty sure it won't go in less than 20 cubic centimetres. Now I start adding very small amounts of sodium hydroxide. Wash down the sides of the beakers in case there's been any splashes. Continuing adding very small volumes of the sodium hydroxide and stopping when I get a permanent pink colour. At which point I record my final volume and work out my first accurate titration. So my first accurate titration gave me a titer volume of 20.9. Let's say my second accurate titration gave me a titer of 20.7. At higher level, those two titer volumes would be concordant because they're within 0.2 of each other. But at advanced to higher level, we expect concordancy to be 0.1 cubic centimetres. So we need to go and do a third accurate titration. If we got the value 20.8, now we do have two results that are concordant. Indeed, we've got three results here which are all, well, the 20.9 and 20.8 are within 0.1 of each other, and the 20.7 and 20.8 are within 0.1 of each other. So in this situation, we take the average of all three results, which will give us an average volume of 20.8 cubic centimetres. To calculate the concentration of the sodium hydroxide solution, well, first thing we have to do is work out how many moles of oxalic acid were in the conical flask. So the concentration of oxalic acid was 0.132. It was 10 cubic centimetres, so 0.01 litres. So it was 0.00132 moles of oxalic acid in the conical flask. Now from our balanced equation up here, we see that 1 mole of oxalic acid reacts with 2 moles of sodium hydroxide. So if we had 0.0132 moles of oxalic acid, we must have had 0.0264 moles of sodium hydroxide in our titer. So the concentration of sodium hydroxide, number of moles divided by the volume, so 0.00264 moles divided by a volume which was 20.8 cubic centimetres or 0.0208 litres, which gives us a concentration of 0.127 moles per litre. So that is the accurate concentration of our approximately 0.1 mole per litre sodium hydroxide solution.